Okay, so yesterday we talked about how to deal with Hess's law when we have an equation that allows us to access the Hess formation. On the diploma, we ask you to do the basic, which is the flip stuff, the spin stuff with the equations, the multiply. We also ask you to do it with this method. And what they do to make sure you can't do it with this method and have to do it with the other one is you basically give you things that aren't on the data table, like that carbon disulfide that we just did yesterday. Okay. So this is just going to be a review of yesterday. I hope you did your homework and you can remember how to do this. What we have here is we want to know the enthalpy change of this reaction. So we want to know the delta RH for this reaction. Now it also happens to be, we could also call it delta CH because this is a combustion reaction to the most common oxides. So what we have to look at, obviously I didn't give you chemical reaction, so we know we're going to do this with heats of formation. So let's go to the data booklet and fill in the heats of formation for the following compound: zinc sulfide, zinc oxide, and sulfur dioxide. Oh, and oxygen. What do we know the heat of formation for oxygen is? Heat of formation for oxygen is 0. It's elements. So O2 is its elemental form. That's where we're setting it equal to 0. Hello. That was not good. That was interesting. So, Jamie, what'd you get for zinc sulfide, or did you get that one yet? 206.0. Ashley, for zinc oxide, what did you get?
Negative 350.5.
And sulfur dioxide, Aurora.
Negative
0.8. Okay, so because obviously the hint is I didn't give you the different reactions to flip and to multiply, you're going to use this concept. I want to know the delta, the energy change for the reaction as it's written, which is the sum of minus the sum of. Now I'm lazy, I'm not going to write all the rest of it in there. But what goes first, reactants or products? Sorry? Products. Really? And it's being picked up again? Okay. So now we have to go back to the balanced reaction. Did I get them right with that one? 2, 3, 1, 1. That's not right. The balancing is wrong, so we're going to have to go back and fix the balancing. I have to have 2 zincs, and I have to have 2 sulfurs, and that gives me 6 oxygens. So I didn't have the balancing done correctly there. I'll have to fix that. So, we have 2 moles of our zinc oxide, each at negative 350.5 kilojoules per mole, plus 2 moles of your sulfur dioxide at 296.8. And I'm going to use square brackets to indicate that I'm going to have to add those. minus, we have 2 moles of the zinc sulfide at negative 206.0 plus 3 moles of oxygen at 0. And in truth, if you leave out the oxygen, because it's 0, it's not a big problem. From there, it's a straight calculator work. So numerically, what did we get as an answer for the change in energy of this reaction? Rory?
I got negative 882.
Units will be kilojoules because all our moles cancel out as I go through. And there's a reason I put my units in. Okay, I don't. Mr. Hovey's nagging me to put my units in. Yeah, I am. Because when you get to university, they're not going to give you equations. They're just going to give you concepts, and you're basically going to do all your calculations by unit manipulation. So things that we learned in math, in chemistry, they don't have a lot of equations anymore. That's why they only give you they don't give you the 19, or I think that's the reason. They don't give you the 19 that you could possibly use on the diploma. Okay. Now this equation here, what's different about this question than that last question? Yes?
We're given the change.
We're given the change of energy. We are being asked for the molar enthalpy, we are asked for the molar enthalpy of formation to determine the molar enthalpy of formation, okay, of chloroform. So what we're asked for is that. We don't know it. We can figure out the rest of this. This is chlorine. It's elemental form, so we have a 0 there. And we need to go, well, I need to go look in the data book for the rest of it.
Oh, I want to give you a quiz tomorrow.
I'm just going to do it on this page here. Corey, what is the molar enthalpy of formation for methane? And for hydrochloric acid, or sorry, HCl gas? Anybody? John?
-92.3.
Thank you. Now, so first of all, this is a level of excellence question because you have to read. This is what we don't know. We know everything else in this or in this concept that I've got written. Forget what the number is. So we have negative 305 kilojoules. Was it 0.0 or was it something else? Okay. For our products, we have 1 mole sorry. I have 1 mole of my unknown. That's what we're looking for. We have 3 moles of your hydrochloric or hydrogen chloride gas. Minus, and we have 1 mole of our methane. Now, where we can make mistakes here is we get everything done this correctly, and then we start to make some mistakes. So I'm going to write down a line. 1 mole times my question mark plus negative 276.9 minus negative 74.6. Okay. So I did drop the brackets. I can gather these guys together. So negative 276.9 minus a negative 74.6. Yeah, minus, really? Minus 202 kilojoules. Now, or add negative 202, whatever you want to do. Now we add your 202 to both sides. Negative 102.7 kilojoules is equal to our 1 mole times our question mark. And then finally, in this case, we're lucky we divide by our 1 mole. It doesn't cause us any grief. There's a reason why I keep doing this, though. We have equals the delta SHM of chloroform. The molar enthalpy. Now, what did I goof up? I messed up. I didn't divide by my mole, so I lost that. And that's what we were looking for, the molar enthalpy of formation, because that's what we're being working with on the right-hand side here. Formation reactions. I might want to put an F there. So the 2 problems, or 2 things that make this type of question difficult. The first is reading this. One of the distractors on your exam is going to be putting the 305 right there. Or sorry, right there. Okay. I'll guarantee you, when this shows up, one of the distractors is putting the 305 as the molar enthalpy of formation of chloroform, because you misread the question. The other mistake, and we do have issues with this because we have different things on this. We occasionally mess up the multiplication and division, the adding, subtracting. Why I took that entire page. Yes, I'm messy, I know this. But I did take that entire page for a reason. Okay, so those people who want to save paper, as much as I'd like to be a tree hugger, they make paper all day. Use as much as you need. So if there are no reactions given to you, you have to fall back on the heat of formation part. If there are reactions, we're going to make it so you can't fall back on the heat of formation. You have to do the flip the equations around, multiply them by a number, etc. And we also talked about stability yesterday. Thermal stability is the measure of how well a substance resists breaking down to its elements under heating. So essentially, breaking down to its elements, that should be bringing up this idea of decomposition. Now, we don't have access directly to the heats of decomposition, but we do have access to the heats of formation for these. So if you could find, Rory, what's the heat of formation for nitric acid?
It is negative 174.1.
Sean, what is it for methanoic acid? 0.0. And Aurora, ethanoic acid.
Negative 484.3.
Stop picking up my head. Dinitrogen tetroxide, Jamie. Now, this is all kilojoules per mole. I'll just put it up here. Okay. So I'm getting these off of, did I make a mistake? Now, the easy part, the simple decomposition is change the sign. Plus 174.1 plus 425.0 plus 484.3 minus 11. Okay. So, which is the most stable? Which requires the most amount of energy to break it apart? Yes?
No.
Ethanoic acid, also called acetic acid. So the most stable is ethanoic acid. The least stable is the one that, in this case, the one that has an exothermic heat of decomposition. So the least stable is dinitrogen tetroxide. So basically all we're looking at here is that's the biggest, that's the most energy that has to be put in. We only have to get this reaction started. So that's like lighting a match to some gasoline or gasoline fumes. You just have to create a spark to get the reaction going. It feeds that reaction itself. And then we can rank the rest of them. We have methanoic. Okay, I can't write on the board for some reason. So methanoic acid is your next one at 525, and then nitric acid as your third in your list from most stable to least stable. So any questions on that? Well, if there's no questions, I'll go get the paperwork I forgot to print out. I'll be right back.
We actually took.
You have an exam scheduled next week for Thursday, which is right in between your physics and your social exam. Oh, I'm sorry. So yes, it's a busy week next week. We didn't double you up. You really need to have exams for a month, right?